Okay, hi guys, welcome back to Engineering and Structural Design. Before I continue, I would like to ask you to like the video, to share and to subscribe on my channel. Thank you. We were talking about application of influence line last time, and today we're gonna continue talking about the same topic. Today we will talk about the response function due to a uniformly distributed load. Last time we talked about the response function due to a single concentrated moving load. So let's start. We have a simple supported beam like this, but this one is a overhanging beam. This overhanging beam. Here we have a pin support and we have a roller support, and here we have a overhanging part. We have our distributed load applied at this portion, and the magnitude of the distributed load, the intensity, is W. The distributed load is away from the origin at the distance x. From the origin to the beginning of the applied concentrated load, we call it A, and then from the beginning to the end is B. This is A. At this point here we call it B, here we call it C, and the point we call it D. So we want to find the value of the response function due to this distributed load. So the first step is to draw the influence line of the response function. We want to find the magnitude. Let's draw the influence line of the bending moment. Okay. So the influence line of the bending moment, it's B. It's B. Will look like this. So this is the influence line of the bending moment at this cross section B. So we know that this is the positive area, this is the negative area according to our sign convention. Okay, let's make a review. We know that for a simple supported beam like this, when you have a concentrated load, no, a distributed load, when you have a distributed load with the intensity called W and then applied over the total length of the beam L. So to find the equivalent concentrated loads due to this distributed load, we every time call it capital Q, and this concentrated load is the same as the area under the distributed load. But since we have a linear distributed load, so we have a rectangular here. So the area under the distributed load will be the height times the length. So the height is the magnitude of the intensity and the length is the length of the total beam. So we get the equivalent concentrated load of this distributed load. We're gonna use the same principle to calculate or to find a way or a value, a solution to apply to calculate the bending moment. So let's consider a simple element called dx. This differential element, we find it here on the distributed load, is this portion. So we know under this portion we will have also another concentrated load, an equivalent concentrated load. But this equivalent concentrated load will be also a differential concentrated load. We call it dP. At that concentrated load, at the point of application, we can find also an equivalent ordinate under the influence line diagram. So this is the corresponding ordinate. We call it y. So at the section B, we want to find what is the moment created at the section B due to this differential element here. So we know that to find the moment is the applied load times the ordinate and the influence line. So since we have all the differential elements, so our moment here, or this moment, our element moment will be dp times y. But you want to know that dp is a concentrated load, but this concentrated load is applied on the length dx. So dp is equal to the magnitude, the height, the intensity of the load times the length, that is dx. So if we replace the value of dp in dm, we get this corresponding value here. dm is equal to w times y times dx. But this is only when we have this element here. We want to find out what could be the total moment created by this total distributed load. We know that this distributed load starts from A to B. So we're gonna integrate our element of moment. So the total moment is equal the integral from A to B, because we start from A to B. dp dx, that dp dx, that is equal to integral from A to B, w times y times dx. This is the value of dp, is this one. This is the value of dm. Okay, if we integrate this value, we get this one. Sorry for this small mistake here. So this is value. So we get the capital M. Since this is the constant, we get it out of the sign integral. We get a by times dx. But we know this value from calculus that this is the area, right? The area under the diagram. So we get the capital M is equal to W times capital A. So this capital A is the net area under the portion of the applied load. So in our case, what is the area? So we know that our load is applied from A to B. So our area is this portion here. So this is A. This is our area. So most of time when you have a distributed load and they ask you to find the magnitude of the response function or the value of any response function, you have just to find first the influence line of the response function, and then you're gonna find the equivalent area under the portion where the applied load or the distributed load is located, and then you calculate the area, and then you multiply the area times the intensity of the distributed load, and we'll find the value of the response function. Thank you for your watching, and then thank you for your attention. See you next time.